Hello, everybody. Welcome to today's current seminar. Today we have two speakers, two talks. Our first speaker is Haoming Shen. He will be giving a talk on accuracy and robustness of weight balancing methods for training pins. Haoming Shen is a master's student at KTH Royal Institute of Technology in Embedded Systems, specializing in control. He holds a bachelor's degree in electrical engineering from Huazhong University of Science and Technology in China. Currently, he is pursuing his master's thesis at EPFL in Switzerland on performance boost with safety guarantees. Additionally, he worked on improving pins training algorithms under the supervision of assistant professor Matthew Bagu at Digital Future and KTH Institute from June to December 2024. With that short introduction, the floor is yours and you can start your presentation.
Okay, thank you. It's a great honor for me to give a presentation about my past work on the algorithm training pins. Okay, let's start it. So today I'm gonna talk about pins in five parts. One from the problem simulation, and then I'm gonna talk about our primal dual algorithm, and we are gonna discuss a little bit about the interpretation for that. And then we followed by the evaluation and also examples. So let's get started. Also, feel free to interrupt me during my presentation if you have any questions. We both know that in pins, they're used for solving PD or ODS. So usually, like it's a very traditional way to there are two ways to do that. It's like first is like from the data-based method, we are trying to minimize some loss, giving some measurement. Another way, and then will become a learning problem, which means we are trying to learn a best theta to minimize the loss. And another method is a model-based method, which is we have some prior knowledge for our system, and then we are trying to model the system, and given some initial conditions, which form our ODE model in this case. So the target for pins is giving some measurement data and giving some measurement data, we're trying to minimize the errors or both on the measurement and also on the initial conditions, such that the system can satisfy the dynamic constraints, which becomes the learning problem under the constraint optimization problem. And here I give a very general ODE or PD problem, which use the characters Frank F here, which is a nonlinear operator stands for PD or ODE problem. And U is the bounded set in RP, which is the space we are curious about. And the gamma here is the boundary of U. And then we have two different variables. V gamma is the initial and the boundary conditions, and V stands for the sublet space in V, which is the function we're trying to get. So in our paper, we only focus on the PD problems to reduce the complexity and make sure it's more easier to show. So our problem can be defined like follows. We are trying to get the optimal theta, which characterize the function v such that the measurement error and the initial error are minimized, but also satisfy the dynamic constraints in this case. So here, it's very general to use machine learning or neural networks. We first to initialize our neural networks with multiple layers and also bias, then apply for some activation functions. So the theta here is characterized by the weights and the bias. And to solve this problem, we can do another reformulation for the problem we have here, which is instead of make sure the operator equal to satisfied all the time, we are doing an integral here, which is kind of a weak formulation, but it's better for solving the problem. And then here is our new problem we need to solve through Lagrange regularization. We can form the new problem here, which we move the constraints, but we are trying to minimize this big arrow lambda function here, which is our loss function. So in our paper, we basically proposed the proposition here under the assumption 1 and 2. If the neural networks have enough neurons, so the optimal value lambda can be made as small as desired. Okay, so here I'm gonna to give very briefly about the proof for the proposition in this case. Assumption 1 and assumption can be rewritten in a mathematical way here, which is exist V belongs to the space H, which means we have a unique solution. And assumption 2 is Lipschitz continuous property, which is characterized by the inequality equation here. So from our the loss function we try to minimize, we can do some tricks in the second term, which is we have a new term here, which we know is 0 because the V here should be the optimal solution. So it's satisfied. It is 0 all the time, so it doesn't change the equality in this equation. And using the assumption 2, we can do the tricks like this to get the inequality from the operator F to the V in this case. And given in the paper in 1991, there's a very useful proposition lemma in this case, which is there exists an epsilon larger than 0. For any epsilon larger than 0, there exists a number n belongs to n and also a theta such that the norm here is bounded by epsilon. So if we use this in our case, so we can remove the integral here and reach the inequality in the end. So in this case, we will say if there's a larger enough neural networks, we know that the loss function L is bounded by this epsilon here, which it could be a very small number. And okay, so like when we have the integral here, of course, like we cannot just solve this problem directly. So it's very trivial to use Monte Carlo approximation to solve the problem in the real life, which is using the d gamma and the du, which are the finite sets to approximate the whole region gamma and u. And then like we just have the primal dual problem formulation. So the primal update, which is we are trying to minimize all the equation here to get the best theta, which is a gradient descent. And while in the dual steps, we are trying to maximize the lambda in this case, which is the Lagrange multiplier. So this is a gradient ascend steps. So if we keep doing this constantly, actually we are solving we are minimizing this loss function by treating the lambda as a variable. So this is it has been discussed in many papers. The one in 2022, there's LB pins, which using Gaussian likelihood in their loss function to penalize the Lagrange multiplier. And also in the paper in 2023, there's using the argument Lagrange relaxation, which by penaltying the norm of the multiplier to make sure the convergence. And another paper is about mapping through from the lambda to a function using the mapping function m to mapping the lambda to another mapping to another space. And also there's a paper in your group like this about the residual-based attention, which also treats the lambda as a variable to solve the pins problem. Okay, so then we'd like to move to our primal dual algorithm. So here is an overview of the pin our primal dual algorithm for pins. Actually, like it's quite long. There's a lot of things, but actually compared to the vanilla pins, we didn't change a lot because for the conditions, if here it just um, uh, to choose to judge when we should stop. And the main things we change is the dual step here from the line 12 to 16, which is a dual update. So if we remove this colored lines here, then we would come back to the vanilla pins. So first, I'd like to talk about the initialization for the neural networks. Here we are using global initialization to initialize our training variables, theta in this case. We know that different initialization can lead to different training results completely. Here is an training example just using vanilla pins. On the left is the true value from the numerical analysis, but the two from on the right, they just using different seeds. So you can see that actually different initialization points would lead to complete different training results, and some of them are good, and some of them are actually quite bad. So this is actually a stochastic process, which means the different initialization or the parameters can lead to a completely different things. So later, I will also explain how we actually evaluate our algorithm given this stochastic process. And then I'd like to talk about another tricks we have here, which is the resampling policy. From my perspective of learning pins of other people's work, I noticed that in their codes, they all usually use one data sets, and it's which is doing a full data, and they keep the data all the same all the time. But in our case, we instead use a smaller batch, which is only consists 100 to 500 data for each sampling. So why we are doing this? Because like smaller data batch sets can lead to more frequent updates. So which help us and also help us the neural network to escape the sharp minima. And also like small batch size can lead to a better generalization because we have more noise in our gradient updates, which means we are less likely to get stuck in one places. And also by doing the resampling policy, we're actually avoiding the overfitting for training data sets, and also save for computational resources to lead to a faster training in our process. And then there's another new things we had in our algorithm, which is the early stop detection in this case. We want to know that because we don't want to over training our neural network to make the overfit on the data set, we want to know, well, when is a good time to make the stop. So here we proposed a stopping criteria, which is from it's more likely. Let me explain the algorithm here. It's basically like between two different sampling instance. At the first one K, we would save the parameters we have, and we computed the output on the validation data set. And then after several primary dual updates, we would like to save the parameters again and see how the neural network has been improved during during the previous training process. And then we like to compute the error between these two. And later, we just it's more like a moving filter thing because usually uh, I can also explain it later. Then, like we compared this error, we computed the mean error for different resampling process. If after 3 to 4 resampling periods, it's become lower than some epsilon, then we stop training. Which is basically the termination algorithm we have here. We also need a new assumption, which is error gradient Lipschitz, which is the maximum between the learning, the alpha here stands for learning rate. And if we have this inequality here, and also the training data, test data set is same as the training data set without resampling, similar before, if we have enough neural network neurons, so the primal dual will terminate almost surely at the step when we have the G theta here, which is the norm in our detection space. Now I like.
Can I ask a question?
Yes.
The statement, if I have enough neurons, how do I
Yes.
interpret that? The number of neurons goes to infinity, or I can have also multiple layers. So I can have a deeper neural network, but with fixed number of neurons.
Usually it's better to have multiple layers, but also with wide enough, because
No, I mean
like
theoretically, not all in practice. Theoretically, what do you mean by that?
which is at least we have 3-layer neural networks, but with larger enough layer, because this is neural network approximation theory, which means like if we have 3 layers with large enough neural networks, the neural network can approximate any functions. So which means we need at least 3 layers, but we also with larger with enough neurons in those 3 layers.
Okay, thank you.
Yeah. And here I will go briefly about the proof we have. Similarly, from the assumption 1, according to the paper in 2028, there's a theory about this which is when the gradient equals when we reach the optimal theta and the lambda, we have the gradient of the Lagrange function, the norm of gradient. The norm of the gradient of Lagrange function is 0, and also the G we have, which is which is this norm term here we had become to 0. And the second term is for the Lipschitz, is similarly as before, is from the Lipschitz continuous properties. And then the error term we are computing will be bounded by the term on the right here, which is the maximum value during this the maximum norm of the Lagrange function during this updating period. Which leads to that the C, which is the actual value we are comparing to the theta here, will be smaller than some epsilon in this case. So through my brief proof before, actually, like we know that if the conditions that the gradient on the Lagrange function is smaller enough, which is also can be a stopping criteria. But however, in the practice, we noticed that the gradient is very noisy, so it always leads to a stop earlier than before the convergence. So that's why also it motivated us to have this like a moving filter from like a moving filter point of view, that we are calculating the mean error for multiple resampling period. So in this case, we are almost sure that our stop condition is not noisy. Here, I'd like to talk about from interpretations for our primal dual algorithm. The first is to explain it from loss landscape perspective, which is a loss landscape is used to see how the optimal solution obtained is changed during the training. So if we get a theta, we can project it into two different direction. So and then we computed the arrow, and then we can get a loss landscape like this. Here are 5 different loss landscape given different lambda initial lambda. So in this case, this is just from the banana pins. We didn't, because the lambda here is fixed number. The 5 of them are using 5 different lambdas. So you can see actually it's quite ugly in this case because there are a lot of local minima, and also it's very hard to see where is the true global minimum. So usually it's because the physics laws make this loss landscape less nice, which means the loss physical laws are more difficult to converge to a certain point of view. So from a curricular learning perspective, our primordial method is to cut this learning problem into several simpler tasks. We learn something from easy to complex. For example, we first to recognize a square, and then we try to recognize different squares, and then we can add to identify different colors. And then in the end, our ultimate target task is to recognize different shapes but with same colors, which is more difficult to do directly. So which leads to a discontinuous loss landscape in this case. So our Pomodoro, instead of directly doing from learning problem 1 to learning problem 4, it's we have some subtasks in the middle, and then we are doing the step-by-step through the neural networks. So it's actually learning from previous optimal solution, which should lead to a better convergence of our problem. So here is the 2 different mode of curriculum learning. One is sequential curriculum learning, and another is parallel curriculum learning. So the first one is sequential curriculum learning is actually doing step by step, but the parallel curriculum learning is trying to learn everything together to learn from different tasks. So it is starting from easier could be we have more chance to be successful in the end, instead of learning a complex problem in the end. So here is instead of learning the problem 4, which is optimal shown in the green, we have different local minima in the end show us in red. So when we start from the learning problem 1, probably we are very far away, but during the process, we are actually gradually to discard the bad local minimum in this case. So so in this case, the cost function is modifying during training all the time. So here is a well-defined curriculum learning problem, which is very similar to what we have in the primary dual case. Another explanation is from the adversarial learning. So the neural networks will generate a possible solution through data during the primal updates, which is a system G here in this case. While there's a discriminator, which is C, shown on the right. This discriminator, it's trying to discard a solution that if that's the solution that validates the physical loss by increasing the physical loss, which is a dual update in our case. So in this case, from the control, because I'm doing things with control, from a control perspective, the primal update on the left is an open loop system, and our primary dual algorithm on the right is the closed loop system. So usually, the closed loop systems are more robust are robust in performance. So which also explain why in our case the primary dual method would be a better choice to do. Yes, basically this is what I talked before, because the discriminator C will penalize a solution that's not suitable for our not suitable for the physical law here. That's why I also explained that before I also mentioned that we have probably I forgot to mention that we are not doing this dual update all the time. It's we doing it for after several prime dual updates, which because suitable updates is very important for the stabilization of the algorithm. If we doing the dual updates too often, usually the algorithm, the neural network probably cannot learn well from the primal updates, and then the whole solution will be failure. Here is the evaluation of the primal dual methods. We are trying to compare with very common algorithms. The first one will be LBFGS. Why we're using BFGS, which is because it is a second order solver and it's usually converted faster and will converge directly to the optimal point. But it requires a good initialization points. And also we are comparing it to the Adam algorithm and also the Adam random. Here, the Adam random probably more difficult to understand in this case because in the primary dual algorithm, we are updating the lambda. So Adam random refers to that the lambda is picked up between 0 and 1 randomly at each dual updates. We are doing this because we want to see how we update the lambda. Will it affect the final results? And also another thing we are comparing is normal training and pre-training. And pre-training in this case is we start with these first order solvers and finish with LBFGS. We will see how our primal dual behave against to this algorithm later in the examples. Here is overview about how we doing this. We initialize our theta for the neural networks, which is a stochastic process. And we are doing this for multiple initialization, and then we train this different theta. We would have a different optimal theta solution. And then we will compute the error between on the test data sets. And for the analysis, we are using a probability perspective. We are using the expectation to stand for the accuracy and compute its variance for the robustness. Yes, here is what I talked before. The error is defined as one from the neural network compared to the true one, and the accuracy and robustness is the expectation and the variance for different initialization theta. So if we trying to plot this different theta we got, we can do it in the box plot. So the median value will be our accuracy, and this IQR will be our robustness. So intuitively, we'd like to have algorithm with a slower, lower. It's like a smaller accuracy and also smaller robust the IQR in this case. Compared when talking about the other weight balancing methods, there are a lot of different others. The first one is annealing in this case. The loss function is a little bit different because lambda they put on the data set, which is the measurement side. And when they're doing their dual updates, they are doing computing this ratio between the max and the expectation. Through our examples, I will show that actually they're pretty good in practice. But however, it doesn't have a very rigorous mathematical proof to show that why it is good. And another one is inverse Dirichlet method. They are sharing the same loss function with annealing. But instead of when updating the lambda here, instead of dividing by the expectation, they do it they divide by the variance, which is they're trying to deal with the vanishing gradient problem in this case. But however, this is not stable because it's intuitively yes, because we are trying to compute the variance given different initialization theta, which of course will lead to more noise in our training. And another one is NTK method, which the loss function is they have lambda on both data and the physical side. And they're doing this by computing the trace of kernel formulated by the gradients. This one has a very good mathematical proof. But however, during our test, we found that NTK methods, they are highly computational burden. All these methods we mentioned compare with, they are not have a very clear definition with multiple losses in the case. However, in my supervisor Matthew's work in 2021, we first used this primal dual method to solve a traffic problem with 9 different losses term, which is pretty good in the end, actually. Okay, so now let's come to the last part. I'm gonna to show you 3 different examples to compare our primal dual algorithm with other methods. The first one is we are trying to solve the Burgers equations. So the picture on the top right is a solution of these equations. We didn't actually show the equation here because I think it's too complicated. But let me explain how it works. We basically sample data from the boundary to form our measurement arrow. And then we would do our sample in the middle to form our physical loss, which means given a boundary and initial conditions, we are trying to reconstruct in this region between 0 and 5 in this case. So there are 2 plots shown here. On the left is the arrow box plot, and on the right is a time box plot. And they are both normalized by dividing the median for LBFGS. So actually in these equations, they are actually quite easy to solve because also from the figure, you can see they are kind of linear in this case. So all the methods, they are performed quite closely, and annealing in this case, they perform the best. And also it's just slightly higher than BFGS, but while the BFGS, they are quite worse in this case. And the primal dual method is almost the same as Adam random in this case, which means in this example, how we updating lambda actually is not very important, but I will show you later, see why it can be a difference. And here is the loss landscape for our primal dual method for this algorithm. You can see like the parameter for the neural networks. It's this green blue line here stands for different parameters for our neural networks. And the one from the top right is where it starts, and in the middle is where it ends. So actually, you can see there's some local minima on the right, but our primal dual method actually trying to avoid it, but directly jump to the global solution. Here is the second example, which is for the Helmholtz equations, and also the picture on the top right is a solution for this problem. So in this case, it becomes a nonlinear, and which is more complex and more difficult to solve compared to the one before. So actually, if we look at the arrow plots on the left, the how we updating the lambda is actually matters because all the primal dual and annealing and TK and also inverse Dirichlet methods, they are all outperformed than our 3 baseline. And this also can be observed for the per training case, which is will be much more better compared to doing LBFGS directly. But however, in this example, the annealing method, it again beats our primal dual method. It has a lower arrow, but also have a lower IQR in this case. And also during computational when it's regarding to the computational time for the training, it's also the training time is also lower than the prime dual method in this case. But however, for the NTK method, you can see that it's actually significantly increased compared to the other method, which because in this case we are doing more sampling, which is around 500 points for each beta for each batch size. So during the matrix computation, in this case, which leads to the NTK, it have to train longer than the annealing and primal dual method. Here we want to see that how the lambda is updated during the process. So here we trained both algorithms for 30 different initialization points, for different initialization seeds for the neural network. And then we compute the confidence interval for our algorithm. So actually, in this case, the primal dual method is will be better than annealing in the terms of it's more stable and more smooth. While annealing a method, it can have a huge jump at the beginning. And also, when we look at when the algorithm converge, actually the primal dual method is converge earlier than annealing method, which for the primal dual, when around 5,000 epochs, we already converge, but for annealing, it needs to wait until 10,000 epochs. And here, finally, it's the final example for my case. It's 1D Poisson equations. We picked this because ideally we thought it would be very easy to solve, but actually when we actually implemented this algorithm, we can see only the primal dual method is still good compared to the baseline algorithm. But the annealing and NTK and also inverse decay method, they are performed quite worse in this case. We believe that why it happens because in this case, the loss on the data set is too easier to satisfy because the loss term in this case on the boundary is only 2 points, while for the physical loss there are different multiple data in between 0 and 1. So that's why when the annealing NTK and the primal dual method, the annealing NTK and inverse decay methods, they are trying to balance in these two results, but because the loss on the data it's to convert too fast, it just can't handle that. While our primal dual method, it's doing step by step by increasing the lambda to panel the physical loss in our loss function. So it has a more smooth training trajectory. So in this case, the primal dual method is better than the Adam and also Adam random in algorithm. And also regarding to the training time, it almost didn't change anything because we already computed all the gradient in the primal updates. So it is we will say like the primal dual method is a very efficient and consistent algorithm, but also have a good performance in this case. So in this paper, we defined the accuracy and the robustness for Ping's algorithm under the probability perspective. And we proposed the primal dual method framework to solving Ping's problem. And we also compared it with other methods and showing that the primal dual method is actually quite consistent and the robustness through 3 different examples we have. And for the future directions we had, we would like to extend the framework to more complex domain to integrate more losses and also to explore the strategy how to tune in the parameters we have in the primal dual algorithm. Okay, so this is my talk. Yeah, thank you.
Thank you so much for your great talk. Now we open the floor for questions. Do we have any questions for the speaker from the audience?
Hi, I'm from Brown. I'm Youngkyu from Brown. I have
Yes.
2 questions. So
Yes.
first one is, can you go back to page 37? Yes, in these figures, if you use the prime dual, then the lambda is just maybe 0.05 or 0.04. But
Yes.
if you use annealing, then even if the annealing converts, the lambda value is very high. It's almost 400.
Yes.
Do you know
This is
any clues?
yes, because probably I didn't emphasize this because the lambda in this case they represent different meanings. The lambda for the prime dual method they are on the physical loss side, but for the annealing they put the lambda on the data the measurement loss side. So if you divide it by the lambda for the annealing case, which is almost compatible for with the prime dual method.
See. And the other is, have you ever tried to solve the high frequency problem? Maybe for the 1D Poisson, you can modify the right-hand side with high frequency data. Then
Yes.
usually if you want to train the neural network with gradient-based method, then we suffer the spectral bias. Then your method can overcome the spectral bias, or?
Sorry, can you repeat again? I'm not quite clear what you want to ask.
I mean, is your method, the primordial method, can overcome the spectral bias to train the
Yes.
neural network?
In general, I would say yes. Because with the primordial method, actually, it's almost same as the vanilla pins. But instead of fixed lambda, we just using a gradient based method to updating the lambda in this case, which help the algorithm to converge to a global optimal. So I would say yes.
I don't think so. Nothing to do with the
Yes.
spectral bias. But I have a
You need to take the Fourier.
I have a question.
Yes.
What's the difference between if I take the paper of McClinchy, if you go there where you have the papers, it's a paper from Texas A&M on self-adaptive weights. Yeah, on self-adaptive weights. This is not this one. You had.
Sorry, probably saying before.
Yeah, it's a paper by self-adaptive weights.
So here.
Where you
Yes.
had the review.
Yes. You mean okay?
Here, on that page. Sorry, on that page.
Yeah.
If you look, what says mapping to function? The McClinchy, a paper by McClinchy and
Yes.
Draganeto. Okay.
Yes.
What's the difference between? So the primer dual seems to me to be a subcase of that paper, because if I take of course they have attention, so for every point has its own lambda. But if you take all points to have the same lambda, you end up exactly with your primal dual method. You solve a minimax problem.
Yes.
It's exactly the same problem. It's exactly so. So your method is a subcase of that method. But by the way, they were the first to a long time ago. If you look at the archive version, they published this in the archive a long time ago. But anyway, I don't see any difference between their method and the primal dual method if you take all lambdas, take them outside the sum, and then because they're all constant, then you get exactly the same thing like you have. Can you tell me any difference from that paper? I don't see any difference.
I would say I would say yes, but they are almost follows the similar way to construct the methods. in this case,
maybe Juan, are you there?
Yeah.
Can you see any difference? Because I cannot see a difference between if you take lambda constant in the in the self-adaptive weight case, take lambda I is all the constant, then you take them out of the sum. So then you get exactly the primal dual, the minimax problem
Yeah,
you're solving.
I think that actually the self-adaptive weights are a bit more aligned with the dual, because if you see the actual update rule that they are using in the paper, can you go to the algorithm?
yes.
Yeah, you see that actually they are not updating it based on the gradient of the loss. They are just gradient calculating based on the residual itself. So if it's something similar, it should be similar to RBA.
Close to RBA, yeah,
Yeah.
close to RBA, yeah,
Yeah.
yes.
So if
I
you
see.
make RBA, put the RBA outside, then that is true. But
Yeah.
but
So it's very
Yeah.
close to your method. If you if you make all the lambdas constant.
Yes. Yeah.
So it's exactly the RBA method, yeah.
Yeah, I would say more or less yes, but in this case we also because because in this case we are trying to give proof for like the convergence in this
I'm not
case.
saying
Yeah.
the proof is very nice, and also the interpretation, the way you try to interpret it is really nice and helps a lot.
Yeah.
But
Yeah.
at the end of the day, it's
I would
similar.
say yes, it's quite similar to what they have in the paper. Yeah.
Yeah. But the first person, I think, to just for historical reasons, the best person to recognize this as a min-max problem was Ulysses Neto Braga, the guy who is a professor at Texas A&M, who gave a talk here.
Yeah. Okay. For me, like actually, I'm not really to check the exact date because I haven't read enough data papers about the history about this Mimax.
No, I'm just
So
informing
yeah,
you.
yeah. Thanks.
It doesn't diminish your contribution. Just that we were definitely inspired by their paper.
Yeah.
Do we have any
maybe
other
now that I'm here, I
questions?
can ask another question. It's about your stopping criteria. So essentially, can you go to, there was like another where you had like the stopping criteria, right? So here what you're doing is like you store your parameters in iteration k, and then you compare what you get in iteration k -1, and if the difference is not too big in some sense, then you stop, right?
Yes.
But what would happen if you like? Well, there are two cases that what I was thinking. Like, what would happen if, because the especially since you have like this really small batch size, your training will be quite noisy. So
yes,
what would happen if by luck you capture these 2 points, and then our network are not doing this?
yes.
Let's assume that this is your sampling k, and this is your sampling k +1.
Yes.
Then your model will tell you stop here, but you could still have gotten below.
Yes. So it's why like we have this. You can see like you have plot here is between k and k +1, which is just one arrow in this case. And then what I do is to doing a mean for multiple sampling periods. So it's in a way to avoid to say that we could have to like from an engineering from a practical way to say that we are trying to avoid this situation. Yes, of course, like the things you say right now, we observed it during my training process. So that's why adding this moving filter stuff, because we are trying to complicate it for different compare. We are using for different arrow in different sampling periods. Then we compute the mean of this arrow. If this arrow is smaller than some epsilon, then we stop.
Well, okay, yeah, thank you. And well, in that case, that comes okay. That was one part, and the other part is like there are sometimes when your training loss does something like this, and it becomes steady. But if you compute the validation error, does this. So in other words,
your training error can be constant, but your validation can still be decreasing. And there are several cases where that happens. So, but I assume that in your case, what would you end up happening is like as soon as you reach here, you stop training because the loss becomes flat, right?
No, because like this gradient in this case is still have it's the Lagrange function. It's not on the it's gradient on the Lagrange function, not only on the data set. You see, like the whole. Yeah.
What I'm trying to plot is this thing. Let's assume that this thing is what is in the red line. This is essentially the loss without the Lagrangian. So
Okay.
yeah. So there are some times when you observe that the training loss got flat, but
Yes.
the error is still decreasing even when the loss is flat. And actually, we have a paper on that. It's called "Learning." We actually linked it to the information bottleneck theory, and the general idea is like of all the papers exactly that you observe these kind of things. Like even though your loss gets flat, your model can still keep generalizing and keep improving the performance. But since you don't have, in other words, your gradient, I understand, would be different for the green line if you would have access to the true velocity while training or the true metric while training, but you don't, right?
Yes, we don't. Okay, so it could happen, but I'm not sure how. Yeah, because like during my implementation, I seldom see this is happening. Of course, you can of course you can like pick I mean a lower epsilon in this case to achieve a better performance in this case. That's why you need like to.
But then it becomes like quite arbitrary, right? And actually, to see it, it's quite easy. And you can just train Alenkern, and then if you train for the first 100,000 iteration, you see that everything is flat. But then after 100,000 out of nowhere, the model converges. And actually, in the normal machine learning side, they relate this to things like this double descent, like your becomes flat, your loss jumps, and then it suddenly decreases. The test error jumps, and then it suddenly decreases again.
Yes, so that's why like if like you're training for the infinite epochs, you are like you're actually like overfitting on your training data set, right?
Not necessarily. But, well, that I think. Well, it's not necessarily true, but what happens is like when you compare, for example, for Alenkern, you do it in the validation data set, right? So
yeah,
because for pings you don't the true solution, the model do not see the true solution while training, right? So what I'm saying that the loss becomes flat, I mean that this is like, I don't know, your PDE plus boundary conditions, but then you can also have like some kind of like metric about how your model is doing if you compare it with the true solution. And then you will see that out of nowhere, after several thousand iterations, the validation error decreases. But in this case, your method will, if you fit here, it will get stuck here because it didn't reach long enough to be able to be able to generalize. Yeah, but yeah, it's related to the thing that you were mentioning to overfitting. But if you want to go to that part, like it's more related to this thing called to double descent. It's yeah.
Okay, that's interesting. I'm not quite sure, like because I never tried to train like for quite a long time for the pings. So yeah, but yeah, probably I'm not sure, but I can have a look at it. Yeah, but for now, like I can't answer your questions.
Okay, yeah. Thank you.
Do we have any other questions, comments for the speaker? It seems that we don't have any more questions. Thank you for your great talk, and thank you for joining us today. So it's time to move on to our second session. Our second speaker is Dr. Shu Chu. He will be giving a talk on OpenFOAMGPT and AI engineer. Dr. Shu Chu is a senior lecturer of data-centric engineering in the University of Exeter, UK, as well as a Privatdozent in University of Stuttgart. He received his bachelor's degree from Tongji University in China and both master's and PhD from University of Stuttgart in Germany. He finished his habilitation between Faculty for Aerospace Engineering and Cluster of Excellence SIMTech in University of Stuttgart. His research focused on data integrated thermofluids. He has published more than 40 journal papers and book chapters on JFM, PRF, POF, and others. Dr. Chu developed the innovative LLM-based agentic AI for CFD, which is OpenFOAMGPT. With that short introduction, the floor is yours and you can start your presentation.
Thank you very much, Nas, for your introduction, and thank you very much, Juan and Professor Kaniatakis, for your invitation. So I'm very glad to be here and give a talk about our OpenFOAMGPT. So this is actually, we are actually a combination of both Great Britain and also Germany. And so I actually spent quite some time doing a lot of DNS and LES, and since about 5 years, and we have some passion for AI for fluids. And basically, so there are three things maybe it's worth it to mention. So the first thing is differentiable fluid dynamics. The second thing is causality analysis, and the third thing is this OpenFOAMGPT that I will introduce today. So to the first thing, maybe so just a little bit introduction of our other works, right? So the first thing is differential fluid dynamics, means CFD with automatic differentiation. Then you get a lot of gradient information. We think it's good choice to do many kinds of inverse problem, especially in a very easy way. And that's why we choose the open source Jax Fluids developed in TU München, and we try to control and optimize this compressible turbine channel flow, right? So, and because we want to individually control all each cells on both walls, that's why it's a very high dimensional optimization and with a lot of state variables. And we try two different kinds of control. So one is opposition control, the other thing is porous media boundary condition. So, and also because the other type of inverse problem we think is very good, very fit for our method would be data simulation. And this is the case we try. So it's compression ramps, right? So with Mach number 6, and we try different objective function like 2D, 3D PIV and Schlieren, and try to estimate the uncertain inflow in the DNS, right? So the second part is previously we actually spent quite some time on the data-driven causality. Yes, and this is more like try to know the cause and effect relationship. It's mostly for the theoretical study, right? So, and of course, many people are trying to use that for control or modeling, right? So anyway, so let me start with the OpenFOAMGPT. And of course, yeah, it's a little bit background. So, and UK, so last year won 2 Nobel Prize, right? So one for physics, that's Gertrude Hinton, and the other one is the Nobel Prize for chemistry, that's Demis Hassabis. So, and of course, US has developed or introduced the most powerful LLM tools such as ChatGPT, Cloud Growth, Gemini, and followed by China, right? So such as DeepSeek or Q1. So, and so if you have used that, you know that's very powerful and it's changing our life. So this already maybe half a year ago. So LLM surpassed human performance on nearly every math and coding test. So we usually think that mathematics and coding indicates the intelligence of human beings, right? So, and if we think LLM as human, so then it must be super smart. So, and myself, a lot of people, so myself, including myself, we have a lot of passion on AI for fluids. So, but to be honest, I think maybe even after 10 years of research, so this AI for fluids still has very limited impact on the industry. So, and we still use the same workflow as long time ago, and the same numerical method, almost the same, right? So RANS, LES, or not even LES, just RANS. So, and also, the current method has almost no link to the LLM. So this is why our goal is try to use LLM to solve problems for the industry and contribute to the society. So as proposals and the first 1 or 2 page, we need to emphasize what is our contribution to the society, right? So that's actually always keep us thinking. So, and I'm not that young, so as you can see, maybe, so since my PhD, so during my PhD, I did a lot of work on the heat transfer of supercritical fluids with OpenFOAM, right? So, and I've dedicated 10 years or even longer, so on different kinds of DNS, LES, including porous media, right? So multi-phase flow, and suddenly, so I'm not very sure, right? So, how can I help people, right? So, how can I help the industry, and how can I help the society? Or so let me, yes. So maybe I just do it, just try to publishing, right? So. So on the other hand, we see so the CFD is a very valuable industry. So that's why so ANSYS can be sold for $35 billion, and Altair so has been bought with $10 billion by by Siemens, right? So and we all know they don't offer the best solution, right? Or the most accurate or any high order method, right? So, but it offers is an easy and efficient CFD solution. So, because CFD is why we need easy things, right? So because CFD is very difficult, so it requires license and support, training, years of experience, right? So a lot of things. And as the most popular open source CFD software, so OpenFOAM, so after 30 years of development, it has now over 1 million lines of code. And because of open source, the documentation is very bad. So in general, it's very bad. And of course, you can find some online resource, right? So, and if you don't know anything, right? So you can go to CFD online, right? Go to the forum, find some solution. Or so if you are a commercial user, so you might go for the consulting, right? So in general, so you need to invest more time than the commercial solver. So unqualified CFD engineers so will cost 100,000 euros, pounds, or dollars per year, or even more, right? So because many people they go to the big tech company. So, and I believe that in the future, so we will have a human AI fusion CFD team, so with a human engineer, so as well as the AI engineer. So, if you think in a positive way, that will be very cool. So, such as you feel like Tony Stark with a lot of suits, and this is what's happening. So, and that's actually the motivation of developing so OpenFOAMGPT, such a LLM-based AI engineer. So we want to use natural language or prompt, and then our OpenFOAM GPT can do the pre-processing, simulation, validation, post-processing, almost. So let's say trying to do almost everything, right? So and of course, it's an agentic system, right? So as many of you already know, and we try to make it adaptive to various large language models, and in general, it's possible. And with, of course, with the development of LLM, so I think the difference between different LLMs will be less and less. So if you use some expensive models such as Open or ChatGPT o1, so or O3, they're really good, right? So, and they are also not cheap because you need to write a lot of input files, especially when your simulation case is kind of complex, right? So, and but you can also use the LLMs from China, such as Q1 2.5 Max, and in all these cases, we test, so the token cost of what the most expensive one, right, is about 2 cents, right? So that's literally nothing. And this is, in principle, our simulation agent. And in general, so it has three parts: the system prompt, user query, and the RAG system. So you can use RAG, so but even without RAG, so it can do a lot of things, right? So, but I believe so for many groups in universities or the companies, they already have a lot of legacy code, so it will not be, or legacy cases, right? So it will not be a bad idea to put all of them in the RAG, right? So yes, in general, so it will largely enhance your performance. So in general, so you have we see actually actually rapidly increasing passions, right, in this area. And in general, so you have two ways to connect to your LLM. The first one is using APIs, or aka the online model. So ChatGPT has a lot of models, right? With some confusing names, right? So, and also Cloud, for example, it's also a pretty good choice, as well as Q1. So, yes, it's actually also quite good. So its performance, and the DeepSeek, we also tried that. So I saw also recently a paper from your group. You also tried some different LLMs, right, for different tasks. So DeepSeek, we think it's a little bit too creative. Sometimes it doesn't really follow your order. So that's why, so if you compare that to the other Chinese model, we then prefer this Q1, right, 2.5. But like I said, so yes, maybe so in half a year or 1 year, there will no difference at all. So and you can also try this local deployment. So university likes that, right? So, and also industry, right? Especially the CFD, some of the industry that are kind of critical, and also yeah. Professor Kanedakis knows what I mean. So, Europe cares a lot about this data security and these things. And there are a lot of things to do if you want to use online models, and it will be a good idea to keep it local, and of course give you data security. And yes, and of course, if a lot of people use together, may also bring you some price advantage, right? So we try to deploy all this so even for this DeepSeek, so it has so many versions, right? So, and their performance varies, and it's also takes some time to deploy, because you need a lot of time to load this, for example, 600 gigabyte model to all the memories. Takes several hours, right? So, and you need at least 8 or even more. So state-of-art GPUs, like 800 or AMD, you can also do that. We tried that. Yeah, it's just okay. So, but again, so many users can use at the same time. So this why. So maybe it's a good idea. So in China, you can find a lot of people trying to sell this local deploy the machines, right, for local deployment and quite, let's say, cheap machines, right? So maybe based on CPU. Yeah, we also try this not the so-called full blood models, right? The small models, QWQ32B. It can actually run on a single NVIDIA, so 4090. Yes, it can, of course, it can be connected to LLM, but we think if you really want to use that, it requires some fine-tuning or post-training. So it is not as smart as the other big models, right? So, and if you use, okay, so let's see, so what it can do, right? So we try, at very beginning, we try some typical engineering tasks. Within, we try some simple cases, let's cavity flow, right? So hot rooms and piece daily, right? So as well as some a little bit complex cases, such as mixer or particle flow. So this our OpenFOAMGPT can help you, for example, alternate some initial condition, boundary conditions, and even because it can write some codes, that's why. So even without any so post training, so it can help you implement some code, right? So, and of course, you can also use that to change the thermophysical properties. So it might sound it might sound easy, but I assume so that's the daily life for CFD engineers, right? So, and it can also help you to change the turbulence models from K epsilon to renal stress turbulence model or some, let's say, not frequently seen turbulence model like KKL omega, right? Three equations. It's not just in open form, it's not just change a name, but you need to set up a lot of initial boundary conditions and numerical schemes. And to be honest, even as a user, so it could be tricky. So sometimes, right? So for examples, of course, this OpenFOAMGPT can help you on some coding, very simple codings. Uh, let's say implement unsteady boundary conditions, and this, let's say, velocity is a sinus function of time. And in OpenFOAM, then you need firstly to pick up the right boundary conditions, right? So, and so I use OpenFOAM since 10 years or so, but as you know, this versions change and now you have two branch. So I don't know. So which even, so if I don't go to internet, so I don't know. So which boundary condition shall I use, right? So, but it's a little bit ridiculous is the agent knows, right? And also wrote me this part of code to try to tell so how to implement the right time, right? So this also not that easy, so I would say. So sometimes it's also interesting that since it has a lot of versions and you want you find some special functions and that might not be available in your solvers or case, right? So or even in the other branch. So these two branch, so the foundation, the ESI, they are not compatible at all, and you need to do some dirty works, right? So to do the code translation. And we pick up four cases, such as T-junction, channel flow, LES, right? And actually, OpenFOAM GPT can help you on that, right? So especially if you use the web version, so it can do one out of four times, right? It's not always working, but if you use the agent, so it actually the success rate is better. Even it doesn't work fully, so it gives you a very good start and some bugs or errors that maybe the OpenFOAMGPT thinks is very difficult, right? So because it has this correction loop, right? It will read the bug and try to correct that. But even though, so it doesn't always can give you the bug-free cases, right? So and okay, many people say so. So there are several research in this field, and they especially focus on some they focus on some like cavity flow things, right? So we think if we really want to use that, so it shall do more. So that's why we test all these cases outside of the tutorial, right? So but these are still quite typical for academia and industry. So we don't use RAG, so we don't use fine-tuning and no additional training. Nothing. We just want to see how it works. So, and you can see like we have some falling droplets or impinging droplet that 2D, right? So because we want kind of fast, but 3D is also more or less the same. And also rising bubbles. So if you go to many groups, right? So in the university, the fluid mechanics, you can find actually a lot of falling droplet, impinging, rising bubbles, right? And of course, it's flow through cylinder and airfoil, right? So, and recently, we just developed another new version, so OpenFOAMGPT 2.0, and it is actually much more powerful than 1.0. And now, so we have end-to-end workflow and truly automated CFD, right? So, and previously we didn't use this multi-agent structure, so because we don't want just have some fancy names, right? So we think it's not necessary. So, but now since we want different tasks from pre-processing simulation to post-processing, right? So that's why we do use this multi-agent framework. And of course, the other thing we want to achieve is systematic analysis. So if for industry, for research, so it's very rare that you just do one simulation. So you need to do parameter study, right? So different density or different Reynolds number, these things, right? So we want to use one prompt, and our OpenFOAMGPT can do a series of simulations, right? A lot of simulations, and give us the plots, right? So all these cases. And so the pre-processing agent can decide whether to use block mesh or snappy hex mesh. One is the manual tool, and the other one is kind of the automatic tool. And we use a CAD file as the input. And of course, you can also connect or use some traditional agent, try to directly use the natural language to generate some CAD file. But I'm not sure, right? So sometimes natural language is not the best to describe a geometry, right? So how can you describe a Mercedes just with natural language? So for the post-processing, it's also fully automated, and we want to do the plots with NumPy or matplotlib. And many people ask, okay, so if this is your agent, right? So you don't touch that. So how can you be certain that it is correct? So of course, like all the scientists, we need to do the validation, right? So here we show you the end-to-end, also the fully automated validation. So no human intervention at all. So for example, this single-phase Poisson flow, right, with analytical solution, or this two-phase Poisson flow also with analytical solution, as well as this Laplace bubble, right? So multi-phase, two multi-phase validation. And we have further, so 4 or 5 evaluations, and so trying to give you the end-to-end results from the prompt to the plots, right? So here, all these pictures are given by the OpenFOAMGPT, and the first one is two-phase pulsar flow, 2D, and we use VOF, it's a laminar case, right? So, and of course, the agent knows, okay, so block mesh is enough. And these three figures are the mesh sensitivity study, right? So, of course, 2D and saturation, right? So how much water you have in this domain, as well as this viscosity ratio. So, and the second evaluation, so is a little bit more so complicated, and actually almost, I think only one of this evaluation is a part of the tutorial. All the others, they are not a part of the tutorial, and you cannot find it on the internet, okay? So second one is single phase flow in porous media. We have this 2D random packed circular geometry, right? So, and of course, so you need some snappy hex mesh, automatic mesh, right? So, and the first test is mesh sensitivity study, right? So we have 5 different mesh, and you see here, we even have this 2% of this range. And the second one is the structure side. The second one is the second test is try to determine the minimal size of this REV, right? Representative elementary volume. So what is smallest size to represent this random porous media. And so the agent did 8 simulations, right? So plot in one figure, right? So, and you can see, okay, what is smallest size plus minus 10%, right? So the third test is Darcy flow, right? So try to examine the Darcy flow. So whether it's a linear function between the flux and pressure difference, right? So if you increase the pressure difference, sometimes it will be the Forchheimer regime, right? Or so-called Darcy regime, right? This 7 simulations. So the other case is also is more complicated. It's a multi-phase flow in porous media, and this is also a quite active research area. So not exactly fluid mechanics, right? So but hydrology, right? So it's hydrology because a lot of many things happens under the earth. So multi-phase flow in porous media, you have this drainage process, right? So for example, if you want to be practical, so that you have the EOR, right? Enhanced oil recovery. So if you want to be so very environmental protection, then you can say, okay, it's a carbon capture utilization and storage, or CCUS. So, but for fluid mechanics, it's the same. And all these figures, you can see they are actually plotted given by the agent. The first one is a study of different contact angles, right? So from 95 degrees to 155 degrees, right? So and the second one is try to increase the velocity and try to see if you can get more effective drainage, right? And third one is viscosity ratio, right? Different viscosity ratio. So these are actually all very practical things because in the application, the oil companies, they always add some nanoparticles or something to try to get more oils, right? That means more money, right? So and the fourth example is aerodynamics of a motorbike, right? So it's a single phase because it's turbulent flow, right? So, and of course it has relative complex geometry, and it's a part of the tutorial case. And we just give the prompt that, okay, so we want to simulate 10 cases, right? So 10 different velocities, and we want to, you just, and you need to give us the drag coefficient, right? So and I show you, so what I emphasize here is an end-to-end process, right? So you just give some orders and you get a result. So The other thing, what really matters for me is a trustworthy AI. So because in general, CFD or any other scientific computing has a zero or low fault tolerance, right? So if you have a typo or missing anything, so it will not work. And so all this LLM, so basically it's a prediction of next token, and we know so hallucination, which means, or you can say it's getting crazy or too creative, right? So even it's you emphasize a lot of time, it doesn't listen to you, right? Or so you can't fix bugs if you give a picture, right? So does this guy look handsome, right? So you ask 100 times, then you get 100 different answers. That's not acceptable for us, right? So it's maybe okay for chatbot, right? So that's why, and we want our OpenFOAMGPT not just end-to-end automated, also no human intervention. We also want to have 100% success rate and to have a reproducible environment, right? And that's why, so you can see, okay, so after the first release, there are several follow-up papers, and so I think so, and even so, even sometimes in our previous results, we find out, okay, so maybe it gets lazy or gets tired, it doesn't work. So that's why in the 2.0 version, so we want to show explicitly, transparently, okay, how many repeat did we do, right? So you can see all these 5 cases, we repeat 10, 12, or 5, because that's because it's kind of expensive. So, and we can actually achieve a success rate of 100% in all these cases. So, and okay, we won't see, okay, so maybe we can do more. It is still very trustworthy. We don't know. So that's why we pick up the single phase flow in porous media. So it's also relatively complicated. And we did 100 same simulations, right? So we try to see whether it gives the same results every time. The answer is yes. And also, and we, in the other test cases, we just want to see, okay, if we give 100 different parameters, let's say 100 different pressure difference, and we want to have one plot, can you do that, right? So without any error, so and very reliable, and just give us the plots, and it also works. So, and I think this OpenFOAMGPT is the world's first AI engineer for CFD, and so it's also quite trustworthy, and it offers an end-to-end approach. So we are very lucky that we feel enormous exposure across social media, so like LinkedIn, so or WeChat, right? So this is this Chinese WhatsApp, and also the others, right? So, and I think we inspired many researchers and industries. So, and of course, many approaches. So, but as you know, is in Europe, and not all the people so like these things, especially in Germany, so kind of conservative. And so one professor says someone could attack you on your way home, so maybe that's possible, right? So guy is taking our jobs with the Chinese AI. So I don't know. I think it's not correct. So even we are lucky to do something correct. So in the end, so most of the money will be earned by Siemens or Ansys, right? So they will take your job, right? So not we. So I think it all prove one thing. So it will reshaping, or it is reshaping how we use computational fluid dynamics. So it's a little bit conclusion. So we developed this OpenFOAMGPT. It's the world's first AI engineer for CFD, and we want to make it trustworthy and give us a very easy end-to-end approach. So, and I think this means a revolution for the CFD engineering. So, and you guys in American, so you must have heard this low code, right? So in computational fluid dynamics, all these things with cursor, right? So Windsor, right? So and more and more code are generated by LLM. So, and what OpenFOAM represents is low sim. So I will, I can predict that in the future, so more and more simulations will be performed by the agents like OpenFOAMGPT, and this leaves as a result of low simulations. So I think that's all, right? So thank you very much. So I'll be happy to take questions.
Thank you so much for your great talk. Yes, George, do you have any question,
Yeah,
comments?
I have several questions.
Yes, please.
So thanks very much for coming to give this talk. So in terms of the implementation,
Mhm.
you you use QN, right? You didn't use ChatGPT. You used QN, you said.
We test different versions. Also, the ChatGPT we use that. Yes.
But the
Mhm.
the one that you have
Mhm.
2.0, what do you have?
Yes. We have the ChatGPT and also I think partially Cloud, but ChatGPT and Cloud, according to our experience, they work pretty well. So Q1 is also good, yes. Yes, it's also you can live with that. So, but this DeepSeek R1 so has some. It's even as not as good as this V3. So we take the temperature at 0. So we don't want to creative or these things. But what but what I think is it develops too fast. So what I say is, so this may be the test made, you know, two months ago, right? So and in half a year it's different, and maybe all these models work quite well, and that's what
Yeah,
I predict,
I
right,
see.
for the next year.
So you want to have all the options open. But
Yes.
okay, so now it wasn't clear
Hmm.
what is the connection of the GPT with OpenFOAM. OpenFOAM, of course, is
Hmm.
an open source code.
Yes.
But so what the GPT does, it takes the prompt and
Yes.
translates it to
Yeah.
something, and then there's an agent that performs some action, and
Yes.
and the action is you show us an example where it can write also the
Hmm.
time-dependent boundary condition, right?
Yes. Yes. Exactly.
But can you ask it, for example, I want to replace the solver with a BiCG stub, for example, right?
With what?
It's just a different method that I like.
Oh,
BiCG
yeah,
stub.
sure.
Yeah, yeah.
Yes,
Okay.
you can, this is relative simple task, right? So you just replace the name. So, yes,
But
yeah,
it has to go and find that algorithm from the Petsy library.
yeah, yeah.
Here's the task. Here's the task.
Mm-hmm,
I'm looking at the Petsy library,
mm-hmm,
and I'm finding a solver, and then
mm-hmm.
I go to OpenFOAM GPT, and I
Yes,
ask it to change the solver for my
mm-hmm,
version
mm-hmm.
to have the best Petsy library solver.
Yes. I think it can do, yes. This is, I think even so, this is a relative easy task according to my experience, right? So yeah, to just change some name, but
No,
uh,
not the name. That's what I'm
yeah,
saying. It's not because it needs to not to actually
no, right? Yeah.
they implement the algorithm, and then the hooks will be different,
Mm-hmm.
right?
Mm-hmm.
Because
Yeah.
but you think it can be done?
Yes, it cannot do extremely long code, long piece of code. Maybe so we didn't test that, but for example, we actually also let it to extend some functions, right? Implement some new models. Let's say so electrothermal models for the battery. Let's say we have heat transfer, so a thermal management for some Tesla batteries. And now we want to implement some thermochemical models. It actually does, right? So, and also without the code itself, the function itself has no bug. Okay, so so of course, then this heat change heat transfer study becomes a little bit complicated and doesn't converge. But I think it's not its fault, right? So yeah.
Okay. Okay.
Yeah.
Okay. I think Kyle has. Thank you very much, Shu.
Yeah.
Okay, yeah.
Mm.
Hi, Dr. Chu. This is Kyle from Brown. I've two questions. First of all,
First.
what is the input data modality to this agent? Does it only support text, or for example, if I have some numerical data or other kinds of modality, can I also let the agent know of all the data types that I have?
You mean so binary data or
Right.
what?
If I want to
Mm.
input some, I don't know, data related to the problem that I want to solve, is the agent able to integrate that data into the process as well?
In general, the answer is yes. But for example, if so, firstly, I didn't test all the things, but I think, for example, for the mesh generation, let's say, sometimes you ask it to give you like maybe so give you a structure mesh of one cylinder, right? So it can do, right? But not like 5 cylinder or a lot of cylinders. This type of data, so a lot of spatial imagination is kind of lacking. So that's my experience. Uh, but so I'm not quite sure. So what other type of data you mean, right? So, but in general, some codes and some functions, yes, yeah,
Okay, I see.
yes.
Yes.
It's highly depending on the complexity, right? Yes. Yeah.
Right. Yes, makes sense. And another question is, so you said you tested different LLMs for the agent. In
Yes.
your experience, does the reasoning models make a big difference from the regular LLMs, like using the O3 of ChatGPT? Is how much of a difference does that make from using the regular version without reasoning?
We think, yes, in fact, we don't think this COT or reasoning model are very good, to be honest. They are usually very creative. They have their own thoughts, and they have a lot of their own thoughts, and it's not. For example, for DeepSeek, this R1 is really bad. So I don't
Okay.
know about your experience, but I think it's really bad. So, but this V3 is much better, right? So you just do what you want him to do. But on the other hand, so this ChatGPT O1 is pretty good. So, and it's for all, it outperforms for all. So yeah, that's why.
Yeah.
So yes.
In our paper, Kyle was actually the first author, and
Mm.
that you mentioned, and we found the opposite. But the tasks were different.
Yes.
We found that the models with reasoning, the ones that you call too creative, you call them,
Yes.
are actually the ones that we prefer because they can decide. For example, they can build a function space that
Okay.
that ChatGPT or one will not. I mean, the standard ChatGPT will not do.
Yes.
So so that's why you didn't want two creative models. We want them to be.
Yeah. Yes. Yes. Depends on your task. As yes. Yeah.
Thank you very much.
You're welcome.
Another question. Yes, Zhanzhang.
Hi, Dr. Zhu. I'm
Hello.
Zhen
Yeah.
Zhang, a postdoc at the Grant Group, and I'm not also a OpenFOAM user. So I'm also use ChatGPT sometimes to help me to write some OpenFOAM code. So my question is, so what kind of techniques do you use to guarantee the output of the LLMs to be correct? You also mentioned there are two major branches, and my experience is if I want to do some very custom jobs, the output
What kind
of
of
the
customer jobs?
for example, to design some coded source terms, to recompile sometimes to recompile the major solver. So I think the output of the LMS sometimes is not correct. So I'm not sure how can you guarantee or increase the percentage, the possibility, of the correctness.
I think you need to design well the system prompt, and of course you need the prompt quality is also important. I'm not very familiar, but I also did similar things as you say. Well, so sometimes even so it doesn't work 100%, so it gives you like 80-90% correct, right? So, and if you know a little bit, so anyway, I think it can save you quite some times. That's my experience, yes. But I don't think it can do all the things currently, right? So I don't think so. But my feeling is I don't need all the things. I don't think you need all the things, right? So it has 2 million lines of code. So why should I use all these things, right? So if you think about so any groups, right? So any fluid mechanics groups, so they just focus on 2-3 directions. So any industries, right? So like the Mercedes, they just build cars, right? Normally, they don't build ships or aircraft, right? That's it normally, right? That's why. So I think, yes, there are quite a lot of room that you can tailor for something, right? So
Yeah. So in this OpenFOAMGPT, did you do
yes.
any fine tune or some fine tune to improve the LLM itself, or
No,
just use it to?
we want to do that. So, but I think so. Firstly, so what kind you mean fine tuning? If you really want to fine tune large models, then it needs a lot of resource and a lot of tricks, right? So, no guarantee that you do some fine tuning, it's better because so all these tech companies, they invest really a lot of time, manpower to pre-train these things. And I think if you say, okay, I want to fine-tune some small models, that's easier, right? So you can do with several GPUs. That can be done, and I believe that can also pop up the performance, right? So I think that's yeah. That's the way, yeah. That's a way, yeah. And I also think you guys are more suitable to do the job than us. Yes.
Yeah. Following up a question is, what kind of problem is more, is easier to be solved by this OpenFOAMGPT? For example, if we just invoke the interface of the OpenFOAM, would it be easier? Or sometimes if we just add some coded function without compile all of the major part of the solver, would that be easier based on your experience?
It depends what you need. I think you can do both, and you can also mix of both. And of course, you can define some functions or use some, let's say, MCP, right? So that's all possible. I believe so. For example, if you use MCP or give really some restriction, right? So for the code, that will be very helpful. Yes.
And last question is,
Yes.
you mentioned the prompt. So if so what kind of prompts that I use? Do you need to, make all of the folders for example, in the control system, or constant as input, or just describe generally use a natural language of the job what you need?
We designed that in the system prompt. Yes.
I see.
Yeah. So because it's otherwise the prompt will be very long, right? So this is a general thing you can put in the system prompt. Yes.
Okay. Thank you so much. I really love this idea.
Thank you.
Thank you so much. Do we have any other questions for the speaker? It seems we don't have any more questions. Thank you so much for joining us today and accepting our invitation. Thank you everybody for joining us today. Have a great weekend. It's time to close the session.
Thank you very
You
much,
too.
Sue. Yeah.
Thank you very much,
Yep.
George. Bye-bye.
Bye.